Hey, how's it going, everyone? Today we're going to have a look at network flows. So, we've had a look at critical paths through networks. Today we're going to have a look at what's called network flows. So, there's a few more definitions to start with before we do anything more. So, first thing we've got what's called a source and a sink. So, a source is the network starting node. So, that's where we start. The sink is called the end or the end node. So we start at the source and we end up at the sink. We've also what's called the flow capacity. So or the capacity. So the flow capacity of an edge is the amount of flow that an edge can allow through if it is not connected to any other edges. We've also got the inflow and outflow. So an inflow of a node is the total of the flows of all edges leading into the node. And we've also got the outflow. So the outflow of a node is the minimum value obtained when one compared to the inflow to the sum of the capacities of all edges. So it probably doesn't make much sense, so we're going to have a look at some diagrams. So first thing, just looking at source and the sink. So my source is going to be my starting node. So we're starting at A, so that's what we'll label as our source. And we go through our network, doesn't matter which path we go, we're going to end up at F. So this is our sink. So all flow commences at A, it is therefore the source. All flow converges on F, indicating it is the sink. Uh, just another extension on that diagram. So I've put some labels on there. So we've got 100 going into F. So we started at A, sorry, into B. Started at A. The inflow is 100. But if we have a look at the outflow, we've got 30 plus 20 plus 80, which is 130. So obviously 130 is bigger than 100. So we got to label the outflow as the smaller of the two values. So in this case, we've got 100. So B has an inflow of 100 and an outflow of 100. Looking at a different example though, I've just changed the numbers on the same diagram. So our inflow is still 100. However, when we add up 30, 20, and 10, we get 60. 60 is therefore smaller than 100. So we take the smaller of the two values. So our outflow is going to be 60. Looking at worked example 10, so we've got to convert the following presented in the, convert the information presented in the table into a network diagram. And we've got to label our diagram with direction and quantity of the flow. So just having a look, we've got labels. There's an R, an M, we've got an F, a W, and a D. So first thing, we've got to figure out our source. So where do we start? Well, we've got R to M, and then we've got M to every other node. So it probably looks like that R is going to be our starting node. And as I said, we've got R to M, so that's going to be our second node. So R to M, what's the quantity? So it's 1000. The next thing is we've got M to F, M to W, and M to D. So there's our three other nodes. So we've got F, W, and D. M to F is 200, M to W is 200, and M to D is 300. So that's essentially the network diagram from the information from the table. I'm just going to do one last thing and make up a sink variable. Now it's not in there It'll make more sense later on, but we need all the nodes converging onto a sync node. So it's just a matter of finishing that. So should have arrows on there as well. So 200, and so this is going to be 200. Inflow is 200, outflow is 200, 300, and 300 as shown. So that's the final network diagram from the table given. So as I said, in that example, there wasn't a location demand E. So it's preferable for a network to have both a single source and a single sink. So we include the demand E to simplify the diagram, and it will become more clearer in the following examples. So another definition, we've got the flow capacity of a network is the total flow possible through the entire network. So that's what we're going to have a look at in the next example. So worked example 11, use the information from worked example 10 to determine by inspection the flow capacity of the network. So if we draw up our diagram again, we've got R, M, F, W, D. We had 1,000 from R to M, 200 from M to F, M to W was 200, and M to D was 300. So if we have a look at this, our inflow or our maximum flow um, for the reservoir R to M, which is our dam, so that's our reservoir, and that was our dam. So we've got an inflow of 1,000, and that's our maximum value. However, from M, it's possible for the reservoir to send 1,000 litres per minute. The maximum flow that the dam can pass out is 700. So just looking at, we've got 200, 200, and 300. If we add them all up, it's 700. So the maximum that the dam can pass out is going to be 700 litres per minute. So we say the maximum flow is 700 litres per minute. Part B, whether the flow, determine whether the flow through the network is sufficient to meet the demands of all towns. So if we have a look at the flow through the marginal dam, that was 700, and the flow demanded, so the flow through M is 700. The flow demanded is what's demanded from F, W, and D, which in this case is the same as just 200, 200, and 300, which we worked out was 700. So just by inspection of the table in worked example 10, all town inflows equal the town demands. The next thing to look at is excess flow capacity. So consider what happens to the system if Rocky Bank Reservoir continually discharged 1,000 litres per minute into the marginal dam while its output remained as 700 litres per minute. So if you have a look at that, all right, we've got 1,000 litres per minute going into the dam, but it's only outputting 700 litres per minute. Obviously, the dam is going to be increasing in its volume. So such flow networks enable future planning. Future demand may change, the population may grow, or new industry that requires more water may come to one of the towns. So worked example 12 will examine such a case. So we've got excess flow capacity is the surplus of the capacity of an edge less the flow into the edge. So worked example 10, we've got a new dairy factory called C. It is to be set up on the outskirts of Dervishville. The factory will require 250 milliliters per minute of water. So again, just quickly drawing our diagram. So from D, there's a new factory. If you remember, we had all those converging onto E. So 300 into D, we had 300 coming out of D, but now we've got a 250 liters per minute extra to account for C. So determine whether the original flow to Dervishville is sufficient. So just having a look at this pathway here, we've got 300 onto D, and now 300 and 250 is 550. So the present network is not capable of meeting the new demands. Okay, we've only got 300 coming into D, but it's requiring 550. So there's not enough to sustain that. So part B says determine whether part B, if the answer is no, there is sufficient flow into is there sufficient flow into the marginal dam to allow for new pipeline to be constructed to meet the demand? So basically, we make a new node C. And its demand is 250, so into it has to come 250. So just checking, we've got a marginal dam the inflow was 1,000, and now the outflow is going to be 200 plus 200 plus 300, and now plus an extra 250. So adding them all up, we get 950. So in this case, it is sufficient to add that extra pipeline. So there's an excess flow capacity of 300 into the marginal dam, which is greater than the 350 demanded by the new factory. The existing flow capacity to the marginal dam is sufficient. So before we had 700 compared to 1,000, there was 300 left over, and 250 is less than that, so that's sufficient. And determine the maximum flow through the network if the new pipeline is constructed. Well, that's just that number up here. So we've got our new 200, 200, 300, and 250 added together gives us 950. So the maximum flow through most simple networks can be determined using just these methods of by inspection. However, more complex networks will require different methods. So we've got a minimum cut, maximum flow method. So we're looking at a cut in a network is a line drawn through a number of edges which stops all flow from the source to the sink. We've got the value of the cut is the total flow of edges that are cut. The minimum cut is the cut with the minimum value, and the maximum flow through a network is equal to the value of the minimum cut. So this will make a bit more sense in the next example. So we've got the network shown, and basically we need to make 3 cuts. The first cut, I'll just draw it a bit bigger. A, B, C, D, E. So making 3 cuts, and if you have a look at this, a cut in a network diagram is a line drawn through a number of edges which stops all flow from the source to the sink. So I need to stop, here's my source, there's my sink, I need to cut all the edges so that it stops all flow from one to the other. So first off, simple one is to do that. So I'm cutting along those 3 edges. Another cut could be the same thing, it's just on the other side. So I'm cutting from the sink, which will cut all the flow from one to the other. And the third one, there's lots of different possibilities. I'll just be consistent with the book, which is a cut through these ones here. So part B says calculate the value of each cut. So this was cut 1. So cut 1. So I've cut A to B, A to C, and A to D. And the value of each of those, A to B was 8, A to C was 3, A to D was 7. So if I add them all up together, I will get 18. The second cut was B to E, C to E, and D to E. Value was 4, 3, and 5. Add them together, we get 12. And the third cut, I'm just going to add the numbers for this one. So I'm not going to write them out. 4 plus 3 plus 7. And should get 14 for that one. Part C, determine the value of all possible cuts to give the value of the minimum cut and hence the maximum flow through the network. So essentially, I've made 3 cuts here. There's other cuts that I can make. I'll just label these so we know which one's which. Alright, so I'll make some more cuts. So systematically, if possible. Okay, similar to cut 3, just the other side. So that's cut 4. The other option is doing the same thing but on that side. So that's cut 5, and last one will be this one here. So that's cut 6. And just working those out, cut 4, 5, and 6. So cut 4 was 8, 3, and 5. Oops. So 8, 3, and 5 gives us 16. Cut 5 was 7, 3, and 4. Add those up, we get 14. And our last one was 8, 3, and 5. which gives 16 for that one. So that's the value of all the cuts. So selecting the minimum flow, the minimum value, sorry, is going to be the maximum flow. So the minimum value in this case was cut 2, which was through BE, CE, and DE. So the maximum the maximum flow through the network is 12. Last example, example 14, determine the value of the cuts made in the diagram below. So the flow from A to C, the flow is from A to C, so that's our source, that's our sink. So the inside of the cut is on the left-hand side where the source node is at A. So cut 1 was D, cut 1, sorry, A to E. Yeah. So A to E was our first cut here. Our next one was A to B, and our third one was D, C. We've also got one in the middle of those actually, so we've got from B to D. B to D heads back inside the cut, so ignore this flow value. The second cut, cut 2, was AE and EB BC and BD and AD. Again, we've got BE heads back inside the cut, so we need to ignore this value. However, we've got B to D heads outside the cut. So B to D heads outside the